The purpose of this lab was to observe the motion of some object that is moving at the same speed without changing direction. I chose to use a can of hairspray for my object. The hairspray is the system, and everything else in the universe is the surroundings. Overall, I found that Newton's second law, also known as the momentum principle, held true with both the observations and the model, in that the change of momentum of a system is equal to the net force acting on the system times the duration of the interaction. I recorded a video of the motion of the object and then analyzed it using Tracker. I then made a computational model based on Newton's second law. Finally, I compared the computational model to my observations. When I analyzed the video on Tracker, I began analyzing it after the can had started moving. I set the origin at the center of the can in the first frame, as shown here, and I oriented the x-axis so that the ball would move along the axis. Because it's a constant velocity, the ball will move in the same direction. I followed the center of the ball at the average position and I marked it in each frame. You can see that here. I used the calibration stick to measure the diameter of the ball. The time between each frame was 1/30th of a second, and the total video time was 2.933 seconds. Next, I constructed a computational model using Python. I specified the object's mass, 0.312 kilograms, the time at the first observation, t equals 0, and the time at the final observation, t equals 2.933. I chose delta t equals 0.033 because there were 30 frames per second in my video analysis. I specified the net force as 0 because velocity is not changing, so v initial equals v final, and this means that the force is also 0. That is based on this equation, and this equation also predicts the new velocity of the object. Here you see the equation for the new position. I also specified the initial conditions for the position here and the velocity. I found the velocity using my tracker data and the change in position from final to initial position divided by the change in time from final to initial time. The graph can be visualized when the model has been run. As shown here. It starts at position 0 and gets more negative as the object moves to the left. Here, I plotted position versus time for the observations, shown in red, and the model, shown in blue, on the same graph. The model shows that as time progresses, the position moves in the negative x direction. The slope is constant. If Newton's second law works, the slope should be constant since the velocity is remaining constant as the object is moving. The graph of the observation's position versus time is fairly consistent with the graph of the model's position versus time. The observation also shows that as time progresses, the position also moves in the negative x direction. This is where the data fits the model well. However, the slope is not a completely straight line. It is slightly curved, as shown here. This represents some uncertainty in the experiment because the object was not moving at the same speed the entire duration of the observation. I tried to choose an interval where the object was not slowing down or speeding up. Also, the surroundings could have exerted a non-zero force on the system, changing the velocity and thus making the slope slightly curved. For the what-if question, if I had flipped the axes, my graph would be going in the positive direction rather than the negative direction. The velocity would remain the same, regardless of the orientation of the axes, it would still be constant. For the what does it mean question, because we started with a constant velocity, we know that F net equals 0. However, if F net does not equal 0, the velocity will not be constant. For instance, if I change the F net vector in the model to 3, 1, 0. And I'll do that here. And I will run it. It still moves in the same direction, meaning it's getting more positive, but there's a curved slope and there's a change in the speed. So the graph is different from the previous model.